Students, welcome to Sunil's tutorial. I'm Sunil Barwani and today we'll be doing this chapter called as EMI. Today we're going to see how a coil rotates in a uniform magnetic induction. Coil rotating in uniform magnetic induction. Right, let's consider that this is your coil which has been placed in uniform magnetic induction. Let's assume that this is my uniform magnetic induction in which the coil has been placed. Right, and the coil rotates about its axis. Let's assume that the coil rotates and moves to a new position. Let's assume that the new position is P bar, Q bar, and the original position of the coil is say PQ. Right? The coil rotates by an angle of theta. Right? And this is your angle. Now, so let's consider a coil rotates from initial position. Consider the coil rotates from initial position TQ to P bar Q bar in time t. Right? Such that it describes an angle of theta. Such that describes an angle of theta. Right? In that case, I can say that theta is going to be nothing but omega t. Right? Angular velocity is angular displacement upon time. Therefore, angular displacement will be nothing but angular velocity into time. Now, in position PQ, the plane in position PQ, I can say that the plane of the coil is perpendicular to the plane of the magnetic field B. Let's assume that the external magnetic field is say B. Right? So I can say that in position PQ, the plane of the coil is perpendicular to the plane of the magnetic field. Magnetic field B. Right? Now, as a result of this, I can say that therefore the magnetic flux is going to be equal to number of turns of the coil, cross-sectional area of the coil into the external magnetic field. So that is going to be the magnetic flux that will be passing through the coil in position PQ. Right? Now, as the coil rotates about its axis, there is a change in the magnetic flux, and hence there is going to be an EMF that will be produced in the coil. See, EMF is produced whenever there is a change in magnetic flux. If I rotate the coil, the number of lines of force passing per unit area will change. The number of lines of force passing per unit area of the coil will change, and that change in the magnetic flux will produce an EMF. I can say as the coil rotates, there is a change in the magnetic flux passing through it. Change in the magnetic flux passing it. There is a change in the magnetic flux passing through it. Hence, an EMF is going to be produced. Hence, EMF is produced in the coil. Right? Now, after time t, the coil is in position p bar q bar, and therefore the magnetic flux, I can say that after time t, the coil is in position p bar q bar, and the magnetic flux passing through it, flux passing through it is going to be equal to, since it has already rotated through an angle of theta and it is no longer perpendicular to the magnetic field, therefore the magnetic flux phi is going to be NAB cos theta, right? That is going to be the magnetic flux in position p bar q bar. But theta is nothing but omega t, therefore phi can be written as NAB cos omega t, right? Now, in that case, at this instant, what will be the EMF that will be produced in the coil? If this is the magnetic flux, I can say at this instant, the EMF induced in the coil EMF is nothing but negative rate of change of flux, right? But flux we have already found out as negative d by dt of NAB cos omega t. Constant comes outside the derivative, so this is NAB minus NAB d by dt of cos omega t, right? D by dx of cos x is minus sin x, d by dx of cos u is minus sin u du by dx. So this is minus NAB minus sin omega t d by dt of omega t, right? So in that case, d by dt of t is 1, omega comes out, so in that case you will get this as minus into minus plus, so you will get this as NAB as it is, omega comes out, sin omega t. Therefore the EMF that is going to be induced in the coil is going to be nothing but NAB omega sin omega t. Now let us assume that let F be the frequency of the coil of let F be the frequency of rotation. Frequency of rotation of the coil. If F is the frequency of rotation, then I can say that omega is nothing but 2 pi F. Right? Please don't get confused. So far we had been using frequency as n. Here I am using frequency as F. So omega is going to be 2 pi F. I can substitute this value of omega in the equation of EMF. So I'll get EMF is going to be nothing but NAB. Omega is 2 pi F sin omega t. Right? So in that case, I can say that E is equal to 2 pi NF, 2 pi F NAB sin omega t. Now let us assume that 2 pi F NAB is equal to E0. Let us assume that 2 pi F NAB is equal to E0. Therefore, I can say that EMF induced in the coil is E0 sin omega t. That will be the EMF that is going to be induced in the coil. Now, the above equation, this particular equation of EMF induced in the coil is not constant. It varies according to time. Right? So, I can say that according to the variations in the value of sin omega t, the EMF is going to change. Right? And since it changes as per the sine value of time, Therefore, the EMF that is going to be induced will also be a sinusoidal EMF. It will follow the sine curve. Look at this EMF, guys. This EMF is not constant. E0 is the constant term here. Sine omega t, as t changes, the value of sine will change. That means the EMF curve will follow the sine curve, right? I can say that the equation of EMF induced in the coil varies according to variation in the value of sine omega t, right? Therefore, I can say, therefore, the induced EMF is called as sinusoidal EMF. As it follows the sine wave, therefore it is called as sinusoidal EMF at any instant. Right? Now, we also know that the value of sine function varies between +1 and -1. We also know that the value of sine function varies between +1 and -1. Therefore, I can say the value of induced EMF, the value of induced EMF is going to vary between -E0 to +E0, right? Now, therefore I can say that the maximum value of induced EMF, the maximum value of induced EMF is going to be E0, but we know that E0 is nothing but 2 pi n f AB, right? Therefore, I can say that the maximum value of EMF occurs when sine omega t is equal to 1. Therefore, maximum EMF is induced when omega t is 90 degree or sine omega t is equal to 1, right? Do we get this thing here? And the EMF, the value of EMF induced is minimum EMF is induced when omega t is 0 or sine omega t is 0, right? So those are going to be my maximum and minimum value of EMF induced. Now the maximum value of EMF that is induced is called as the peak EMF. You can say that the maximum value of EMF induced is called as peak EMF, right? So depending upon the variation of omega t, you are going to have EMF that will be induced this way. I'll just show it to you. Let's consider theta is equal to omega t. It can have values say 0, 90, 180, 270, 360. Right? EMF induced. If I use the equation EMF is equal to E0 sine omega t, Sine of 0 is 0, sine 90 is 1, so this will be E0, sine 180 is 0, minus E0 and 0. If I were to represent this graphically, then I would get a wave like this. A sine wave where this value would be minus E0, this value would be plus E0, this is 0, time varies here, this is 90, 180, 270 and 360. So those are going to be your different values, right? Now, I can say that from the graph it can be seen that during half the rotation of the coil, the induced EMF is positive, and during the other half rotation of the coil, the induced EMF is negative. It reverses its polarity, right? I can say that from the graph it can be seen that for half the rotation of the coil, the induced EMF is positive, and during the other half rotation of the coil it is negative. During the other half rotation it is negative. So during first half rotation it is positive and then it is negative, right? Therefore this is called as an alternating EMF. Therefore I can say the induced EMF is called alternating EMF. Fine, do we get this in here? And the frequency of rotation of the coil is called as the frequency of alternating EMF. The frequency of rotation of the coil is called as the frequency of rotation or frequency of alternating EMF. Right? I hope you all know that in India the frequency of alternating EMF is 50 Hz. That means the coil rotates 50 times per second. Fine, do we get this thing here? Symbolically, how do I show a coil rotating in a magnetic field? Symbolically, it is represented as, this is how you represent an alternating EMF produced by a coil rotating in an external magnetic field. How do we get this in here? So now we know how an alternating EMF is produced and why is it called as an alternating EMF. It is called as an alternating EMF because for one half cycle of the coil's rotation, it is the EMF induced is positive, and for the other half cycle of the rotation of the coil, the EMF induced is negative. Right? Now let us see how does this alternating EMF react to resistance. Let's consider a simple AC circuit with resistance. Let's assume this is the current that is flowing through the coil. This is your external resistance R, and this is your E, which is going to be nothing but E0 sine omega t. Right? That's a simple AC circuit with an external resistance in it. Right? So I can say, let us assume that an alternating EMF is applied between the terminals of a resistor. Consider an AC applied to a resistor R. Right? Now, I can say that I can apply Ohm's law to this. If I apply Ohm's law to this, I can say that the current at any instant can be given by the value by applying Ohm's law. I can say that the current at any instant R is going to be nothing but E upon R. Current by Ohm's law is nothing but E upon R. But what is E? E0 sine omega t. E is nothing but E0 sine omega t upon R. Right? Thus I can say that I is E0 upon R sine omega t. But E0 upon R, EMF upon resistance is nothing but current. So therefore I can say I is equal to I0 sine omega t. Thus the current at any instant in an alternating circuit can be given by the formula I is equal to I0 sine omega t, where I can say that I0 is nothing but E0 upon R. Fine, do we get this thing here? So that's how you find out the current in an alternating circuit. Now let us find out the phase in an alternating circuit. What kind of a wave is going to be produced due to the current? If it's an alternating EMF, what kind of a current is going to be produced? Right? Let's find out the phase angle here. I can say as the EMF changes, you will have the EMF changing. The current in the resistor also changes. Current in the resistor changes from plus I0 to minus I0. As the EMF changes from plus E0 to minus E0, the current will change from plus I0 to minus I0. Moreover, the current is maximum at the instant when the EMF is going to be maximum. I can say also current, obviously, because I0 is E0 upon R. If E0 is maximum only, then I0 will be maximum. Also, current is maximum when EMF induced, when EMF is maximum, right? Again, I can say that the current is 0 when the EMF is 0, and current is 0 when EMF induced is 0. Thus, from this discussion, we understand that the current in the circuit is in phase with the EMF. That means the angle between the current and the EMF is 0. The phase difference between them, the difference between the angles of rotation is going to be 0, because the current is maximum when EMF is maximum, current is 0 when EMF is 0. I can say therefore in this case, the current in the circuit is said to be in phase with EMF. Fine. So thus, if alternating EMF is applied across a resistance, and alternating current will flow through the resistance, the maximum value of the current would be called as the peak value of current, which we have already found out, I0, which is going to be nothing but E0 upon R. Fine, do we get this in here? I can say thus, when alternating EMF flows through R, through external resistance R, and alternating current is induced. You will have an alternating current flowing through R. Fine, do we get this thing there? I can say that the maximum value of the current is called as the peak value of the alternating current. The maximum value of current is called the peak value and is equal to I0, which is equal to E0 upon R. Right? That is going to be my peak value of current. But we know that E is nothing but E0 sine omega t. The EMF induced in an alternating current is given by the expression E is equal to E0 sine omega t, and we also found out that the instantaneous current in an AC circuit, right in the beginning we found out as I0 sine omega t, right? So we have also we can induce from this that EMF and the current both are in phase. That means both will be maximum and minimum simultaneously. Both will have maximum value and minimum value simultaneously. Fine, do we get this thing here? So do we understand resistance in an AC circuit? Now once you have this, let's find out something else. Let's find out the peak value and the RMS value. Peak value and root mean square values of alternating current and EMF. Now, when an alternating EMF is applied across a pure resistor, at any instant the current will be given by, you can say when alternating EMF is applied, when alternating EMF is applied across a resistor and alternating current is induced, current flows through it. Right? Now if E0 and I0 are the peak values of EMF and current, if E0 and I0 are the peak values of EMF and current, let us assume that, right? In that case I can say that in an alternating EMF the current reverses its direction every half cycle, hence the average value of EMF and that of current individually is 0. If it's an alternating EMF, every half cycle the current would reverse its polarity, the EMF would reverse its polarity. If I take the average value of both the cycles, the average value of both the cycles will come out to be 0. I can say as alternating EMF and current reverse their direction after every half cycle. Reverse their direction after every half cycle. Therefore, the average value of EMF and current is individually zero after one complete cycle. Therefore, the average value of EMF and current is individually zero after a complete cycle. Right? Therefore, but we know that in a moving coil voltmeter or ammeter, they measure the average value of the voltage and current, and the moving coil galvanometer and voltmeter do not show the average value to be zero. If I connect a voltmeter or an ammeter in an AC circuit, it does not show me zero value. It does not show its value to be zero. It shows a certain value. Right? Theoretically speaking, the average value of EMF and current flowing through the coil or flowing in an AC circuit should be zero. But when I practically measure it using a galvanometer, it does not show zero deflection. It does show some deflection. This shows that there is certain amount of EMF, average value of EMF and current that is flowing through the circuit. Right? Now, let's see this. From where does this value come? Right? I can say that complete cycle is the average value of EMF and current is individually zero after a complete cycle, but a moving coil voltmeter and ammeter. A moving coil voltmeter and ammeter measure average values of voltage and current. Right? That means this shows that the moving coil instruments cannot be used ideally, if it is showing zero, that means I should not use moving coil voltmeter and ammeter in an AC circuit, because if the average value of EMF and current is zero and these measure only average value, these do not measure the peak value, they are going to be of no use to me in an AC circuit. Right? Now, let's try to see how do we measure a voltage and current in an AC circuit. What we know is, we know that there is something called as heating effect of electric current. So, the measurement of voltage and current is done on the basis of this property. We use the property of heating effect of electric current to measure the EMF and voltage in an AC circuit. I can say that heating effect of electric current is independent of the direction of the current. The heating effect does not depend upon which direction the current is flowing through. Once current flows through the coil in either direction, the coil is still going to get heated, right? Now the heat produced in the coil is going to be directly proportional to the square of the current. Also, heat produced in the coil is directly proportional to square of current. Right? Now, whether it is positive or negative, it is always going to be equal to square of current, and this property is used for measuring alternating AC, EMF and current. This property is used for measuring AC, EMFs and current. Right? Now, let us assume that, guys, an alternating current has peak value I0 and is flowing through a resistor R, and the heat produces H in time t. Let's assume that alternating current has peak value I0. Let us assume that alternating current has peak value I0 flowing through resistor R and produces heat H in time t. Right? In which case I can therefore say that the steady state current at constant magnitude, which produces the same amount of heat in the same resistance, is called as the effective or the virtual or the RMS value of that alternating current. Right? If you have this current flowing through the resistor, it is going to produce some amount of heat. Let us also assume that if I had a direct current flowing through the resistor and same amount of heat is produced, let us assume that some value of direct current flowing through that resistance produces the same amount of heat. That would be the effective current that would be flowing through an AC circuit. That means the effective current flowing through an AC circuit would not be zero as we had initially said. Although the average value is zero, but since the resistor is getting heated, that means there has to be some current that is producing that heat. Right? I can say that the steady state current of constant magnitude which produces the same amount of heat that means instead of an AC current, if I had a DC current flowing through the circuit and if same amount of heat was to be produced, the value of that DC current would be the effective value of the AC current that is going to be flowing through the circuit. I can say that the steady state which produces the same amount of heat in the same resistance in the same time would be the effective or RMS value of current flowing in the circuit, denoted as IRMS. Right, guys, I have this AC circuit. I have AC current I, small I, flowing through the external resistance R. if small I flows through the external resistance R, small I is an alternating current, right? Now alternating current is going to reverse polarity. Even if it reverses polarity, it is going to induce some amount of heat H in the resistor R in time t. Let us assume heat H is induced in time t. Now instead of using an AC circuit, I use the same resistance and I use DC current. If I use DC current, what should be the magnitude of DC current in the same resistor in same time that will produce the same amount of heat? That value of current is called as the RMS value of current. Do you understand why we did not directly measure this? We did not directly measure because the average value of current would be 0. And why would I be able to get current here? Because here we are measuring current using the heating effect property, which is independent of the polarity of the direction of the current. Right? Do you get this thing here? So do you understand how I get this? Now, the current that would flow in a DC circuit would produce the same amount of heat that would be produced in an AC circuit would be called as the RMS current. Now, mathematically it has been found out that the relationship between the RMS value and the peak value of an alternating current, the relation between RMS and peak value, the relationship between RMS and peak value of an AC current is given by the formula IRMS is nothing but I0 upon root 2. So when I divide the peak value of current by root 2, what I get is the RMS value of the current. In the same way, the relationship between RMS and peak EMF in AC circuit is given by ERMS is nothing but E0 upon root 2. Right? So that is your relationship between peak current and RMS current, and similarly that's the relationship between peak EMF and RMS EMF. Fine, do we get this in here? Right. We will stop this here for the day. Thank you very much.